In this video, we are going to take a look at chapter 8.7. Please start working on your homework as soon as you finish watching this video. So chapter 8.7, we are going to cover how to measure the heat of reaction or enthalpy change using the standard enthalpy of formation. Okay, so in the previous video, we're looking at how to calculate the change of enthalpy using calorimetry and also Hess's law. In this case, we're going to take a look at the standard enthalpy of formation. Okay, so what do I mean by that? Okay, so we're just going to talk about that soon. So the OER textbook that covered this chapter is going to be under chapter 8.7. Okay, so you see the not sign before in the previous video is literally a symbol indicate the standard state condition, which is at 1 atm pressure and temperature of 25 degrees Celsius. And the reason why we need to have a standard state condition is because this is going to be set as a reference point, and we are going to use pure element to help us to set that as the reference point. So similar to what I mentioned in the previous video as well, elevation, right? So in order we know, for us to know what is the elevation, we need to set the sea level as the reference point, and anything above that would be, you know, like a certain altitude that you are at. So similar to this as well. So for the delta H formation, we are going to use the pure element to be our 0 point or our reference point at this temperature and pressure condition. Okay, so what do I mean by that? Okay, so let's take a look at standard enthalpy formation of different thing. Okay, so before we get into that, let's take a look at the definition real quick. Okay, so the delta H naught F, which is the standard enthalpy of formation, is the change of enthalpy when 1 mole of compound forms from its element in their standard state. Okay, so what do I mean by that? Okay, so let's take a look at this. So for example, if you have let's say carbon monoxide is being formed, 1 mole of carbon monoxide is going to form from its element, right, which is carbon and oxygen, right, in their standard state. Okay, so that means those elements that are going to compose to form compound, those elements would in their standard state would be the one that is going to be set equal to 0. Okay, so for example, in this case, bromine 2 in a liquid form, that is the standard state at 1 atm pressure and 25 degrees Celsius, bromine liquid is going to have 0, which is going to be the reference point, right, for the enthalpy of formation, standard enthalpy of formation. Okay, so same thing for calcium solid as well, graphite solid. So all of these are the elements in their standard state. Okay, so those are going to be 0. We're going to set those as 0, which is the reference point. So that means in this case, if you're looking at all of these, right, those that are 0, it just means that those elements is already in their standard state. Okay. Now you might ask me, hey, I see something. Let's take a look at this. What about there are 2 sodium though? How come that one sodium is 0 and the other one is having a number with it? Well, it's just because that in the standard state, sodium is present as a solid, right? So therefore the solid would be given 0, and the gas form would not be 0 because gas form is not at the standard state. Okay, so therefore there'll be some heat that associated with that, associated with making sodium from solid to gas, right? And the amount of heat that involved would be 107.5. That's what it means. Okay, so is that clear? So same thing with carbon as well. If you're looking at this, right? Carbon graphite versus diamond, right? So that means carbon in their standard state, which is in graphite form, is going to have standard heat of formation equal to 0, right? But if you want to make that to become diamond, right? So the heat that involved with going from graphite to diamond, right, that is not in a standard state would be 1.88, right, kilojoule per mole. That's what it means here. Okay, so if you want to go from here to here, right? So because we use the standard state as the reference point. So now let's take a look at so I want to point out one more thing. Okay, so all of these values are in the appendix 1 in the OER textbook. Okay, so let's take a look at what are the elements in that standard state. Okay, so that have the 0 kilojoule per mole as their value. So those would be atomic element, right? So lithium, sodium, potassium, and these have to be at their standard physical state as well. For example, most metal would be in what? Solid, right? Except mercury, right? And then molecular element would be the one that I asked you to memorize from 121, right? So which is the what is it? Have no fear of ice cold beer, which is hydrogen, which is all of this, right? And then there will be more of molecular element that I did not ask you to memorize would be sulfur and potassium. Okay, so this list right here are given in 121. Okay, so you will need to know that all of these in nature they appear as molecular element. Okay, so they come as a diatomic molecule. All right, so as you see again, so all of these would be zero, right? So all of these molecular element and in their standard state would be zero, as I mentioned earlier. Okay, so let's take a look at how can we write the definition of this. Okay, so I'm going to look at in this case propane. Okay, so this molecule is the molecule propane. Clearly, molecule of propane is made up from carbon and hydrogen. So therefore, in this case, we need to look at the element that made them up, and we are going to use those elements as the reference point, right? And the energy that associated with that would be of the propane. So in this case, we have propane C3H8 gas, and the delta HF, or the standard enthalpy of formation of this, is going to come from, right? By definition, in order to make 1 mole of this, it's going to come from the element that made this up, which is contain carbon graphite, right, in that standard state, and hydrogen too. Okay, so as we see, because we have 3 carbons, so therefore I'm going to add 3 coefficient in front of the carbon graphite, and because we have 8 hydrogen, therefore I'm going to add 4 hydrogen in the 4 hydrogen molecule, right, in order to make 1 mole of this. Okay, so again, by the definition is the heat that involved with making 1 mole of this substance. Okay, so I would like you to take a few minutes here and write the equation involved with the standard formation of calcium carbonate. Okay, so let's take a look at what are their standard elements and how to make it. Okay, so in this case, let's pause the video and then resume again when you finish. All right, let's check your answer. So again, because standard enthalpy of formation is the enthalpy of formation of that molecule, right? So we are going to want to know of this one. So that means in this case going to be product, because we want to make this, right? Because it's involved with the heat that involved making this from its element in that standard state. So in this case, you are going to get, if you look at the table, the calcium that has 0 is going to be calcium with the solid. Okay. The carbon that have the 0 value is going to be carbon graphite. Okay, and then we have oxygen O2 as its standard state. Okay, so in this case, all you need to do is make sure that all of these add up, giving you 1 mole, okay, of this one. Okay, so that means in this case, you are going to make sure that you add proper coefficient. So in this case, you are going to add 1.5 oxygen in order to make it to be 3 oxygen on this side. Okay, so again, the reason why we can leave it as fraction here is as the decimal place right here, not a whole number, is because by definition is the amount of for the enthalpy of formation is by definition is per 1 mole of the substance that you are concerning. Okay, so in this case would be 1 mole of calcium carbonate. So that's why we can leave this as not a whole number. Okay, normally you have to make it a whole number, but except this section right here. Okay, so go ahead, do SO3 real quick. Okay, so again, how do I know what would be standard state? Okay, so that is going to be what is listed on the list. Okay, so I'm going to go back real quick right here on the table that we saw, right? So in this case, the reason why I choose graphite because it's giving me 0. The reason why I choose this calcium because that is in a standard state, right? Same thing with O2 as well, is the standard state, which is at the reference point. Okay. All right, let's check your answer. With the sulfur trioxide, okay, so you are going to make sulfur trioxide 1 mole, therefore you're gonna need sulfur subscript 8, right? Because that is part of the molecular, what do you call, like, element, right? As I mentioned earlier, so you need 1/8, which because you eventually want just one sulfur here, and then we need 3.5 of oxygen. Okay, so check your answer. You can answer this in decimal form as well, that's fine. Okay, so or leave it as fraction, that's fine too, like fractional form or decimal form, that's okay with me, as long as the final product is per 1 mole of the final product for this concept. Okay. All right, so measuring enthalpy of the reaction from, we are going to use this value. Okay, so how are we going to use that? Okay, so first we need to understand what it is first. Okay, so if you're looking at the chemical equations or reaction, it's going to go from reactant to product, right? So you are going to have two scenarios where reactant has lower energy than the product, or another scenario would be reactant has a higher energy than the product. Either way, if you're looking at this, you're going to see that what we are looking at, the change is always going to be final minus initial. So that means you're always going to set up product, right, minus reactant. Doesn't matter which one has higher energy or which one is less, but it's always going to be final minus initial, which is final is the product, right? And then the initial is always going to be the reactant, right? So in this case, if you do that, you are going to use the summation of the enthalpy of formation of all of the product. If you have several products, right, you add all of these delta HF together. Okay, so you're gonna get the summation. So this sigma is the summation of that. Okay, N is telling you about the amount of product that that you are looking at. Okay, so which is in this case, you are going to take a look at the coefficient. Okay, and you are going to subtract with the summation of all reactant involved with that reaction. Okay, the difference between these two is going to be the change of the enthalpy of the reaction. Okay, so remember that the HF is for a specific compound, right? As we look at earlier, it's for specific compound. If several compound are part of the product, you add all that together. So that way you're gonna get the summation of the HF of the product. Same thing for the reactant as well, right? And then you do the difference between those two. Now, if you do the difference, you will see that for the reactant that have lower energy than the product, eventually it's going to absorb heat in order to convert to product. So therefore, you are going to see the positive value of the delta H reaction to be positive. On the other hand, it's going to be the opposite, which is exothermic, if you have a higher energy for the reactant than the product, right? So we talked about this before. It's the same thing that we have been mentioning over and over for the past videos. Okay. Oh, by the way, so this equation right here would be given on the exam. You just need to know how to use it. Okay, so now let's take a look at how to use it. Okay, so let's take a look at this. Okay, so this problem right here is actually the same problem as what we did in on page 21, section 8.6. Okay, so we did this before using Hess's law. Okay, so this is number 2, page 21, section 8.6. So let's take a look at this. I'm going to use standard enthalpy of formation to determine this overall change of enthalpy. Okay, so what do we do? Okay, so what the keyword is standard enthalpy of formation. So circle that down. If you are given the word use standard enthalpy of formation, it means that you have to use this value. And this value is going to come from the given list of those. Okay, so in this case, if you look up the value, you can actually calculate for this. Okay, so let's take a look at how I set it up by using this equation. Okay, so pretty much you are going to use the product, right? So this is product. Okay, because the coefficient is 3, so that would be n. So n is referred as coefficient. Okay, so this n is the coefficient. So we have 3 of them. So we are going to multiply 3 by the value of delta H of formation of NO, right? Because it's of the product. Then after that, you are going to minus, okay, the reactant contain 2 of them. Okay, so it's contain N2O. So the coefficient of this is 1. So that's why we're going to look at this value and multiply by 1. And then you're going to add, right, because this is the summation. Okay, this is a summation. The summation is you are going to add to another species, which is NO2. So in this case, the coefficient of NO2 is also 1. Okay, so next thing, all we need to do is look up this value. Okay, so it's going to be given on the exam. Okay, so if you look it up, it's going to be this value right here. So again, this is going to be in your lecture manual, and also some of this is also part of the OER textbook in the appendix 1. Okay. So all you have to do next is to just add this together, right? And then subtract from this value right here. So this value, if you multiply this together, you're gonna get this value right here, which is going to contain 3 sig fig. And the last one, you do addition right here, is gonna come out with 1 decimal place. The last operation is subtraction. So it's gonna go by the least number of decimal places, which is gonna based on this 3 sig fig, right? So it's gonna be 0 decimal places. So your answer come out going to be 159 kilojoule per mole. Okay, so let's check your answer, or let's compare your answer. If you compare this value with the value that we calculated earlier from Hess's law, which is from page 21, you are going to see that from what we calculated in page 21, we got 157.6. If you're looking at the margin of error, these two are within like 1 kilojoule per mole margin of error. So these two are acceptable. Okay. So that means they are like very similar in this case. So that means it doesn't matter whether you're using the delta standard enthalpy of formation to calculate for the overall change of enthalpy of reaction, or you use Hess's law. They are, if you are looking at the same reaction, it's gonna give you pretty much almost the same value. Okay, so it might be a couple kilojoule per mole different, but within that given margin of error, it should be like similar. Okay, so let's take a look at number 2. Okay, so in this case, I'm going to do the same thing. Okay, so we're going to use the table on page 24 to help us calculate for the enthalpy of reaction that involved with combustion of ethanol. Okay, so in this case, combustion of ethanol is going to come from ethanol, right? Combust in the presence of oxygen, and it's going to generate water and carbon dioxide. Okay, so we are going to make sure that we have the correct balance equation first. So I'm going to balance off those. Okay, so then in order to find out the enthalpy of reaction, we're going to use the enthalpy of formation, right? That's what it's asking us to do. Okay, so it's asking us to use this information right here. So therefore, in this case, I'm going to start with 3 that come from water, which is the product. Okay, so we need to do the product first, right? So we have to do product minus, so this is product. Okay, so this is reactant. Okay, so therefore, in this case, you do 3 come from the coefficient of water. Okay, so add to carbon dioxide, which is 2 of the enthalpy of formation of the carbon dioxide, minus or subtract, right? And then it's going to be this term right here, the addition of the oxygen and ethanol together. Remember, oxygen is already in its standard state. So therefore, that's why you are going to see the value of the HF equal to 0 because of that. Okay. So in this case, if you calculate off this value, you are going to get negative 1,366.8 kilojoule. Okay, so this is going to be the same as what we see earlier. Okay, so this is what we see earlier from I think the section 8.4 when we did the lecture demo, right? So I mentioned that, hey, this number right here, just hold on to this because we're gonna calculate where it is coming from later. So this is where it's coming from. This delta H combustion, or the heat of combustion, is coming from how you use this delta H of standard enthalpy of formation to calculate for it. Okay, so this is what it's from. Okay, so this is part of chapter 8.4. Okay, so this comes from chapter 8.4, page 15. Okay, so that's where this number coming from. You want to go back to your lecture manual, page 15. Okay, so this is where the number coming from. It's come from the calculation using the standard enthalpy of formation. All right, so the summary of this chapter would be pretty much, if you are so 2 things. One is you learn how to write equation of a certain compound that is being formed. 1 mole of this compound that is being formed, right, from its standard element in their standard state. Okay, so the heat that involved with that would be the heat for generating this, because we set off this equal to 0. Okay, so the second one is you utilize this value of the standard enthalpy of formation to help us to actually calculate the enthalpy that involved with the reaction, the overall reaction. And you are going to use this standard enthalpy of formation from the given table on the exam. Okay, so more practice of this would be on the paper homework 8.5 to 8.7, number 7 to 8. Okay, so for example, in this case, 1 is you are going to write equation, right? So this is what we described earlier at the beginning of this lecture video, how to write the equation, chemical equation for that. And then the second part, which is right here, is going to be involved with the calculation of the delta H of the reaction that we just went over. Okay, so please start your homework as soon as possible. And if you have any question, please do not hesitate to email me or attend office hour.